Okay, so in this video, we're going to be looking at some general properties of matrices to get ourselves familiar with how they work. So matrices are described in terms of two dimensions. They're represented by the number of rows and the number of columns. So in this example, we have row 1, row 2, and row 3, and then we have column 1 and column 2. So this would be described as a 3x2 matrix. When we want to specify an entry in a particular matrix, we have a variable with subscripts, and the subscripts are going to represent the in order row and then column. If we are dealing with small matrices, as we usually do in either algebra or a linear algebra class, then we usually don't have to worry about dimensions that have 2 digits per dimension. If you do have 2 digits per dimension, you can put a comma between the entries. You'll notice this if you're using your TI calculator, that they will put a comma because they do allow you to get into 2-dimensional size matrices where there are 10 or more entries per dimension. And so they put a comma there just to clarify. But in most of the cases where we're doing matrices by hand, we have only 3 or 4, maybe 5 entries. And so everything is a one-dimensional number, one-digit number. And so we don't bother with the comma in those cases. So A11 would be considered first row, first column of our matrix. And then the subscripts follow that way. So as you go down the column, then this would be the second row, first column. So it'd be A21. Third row, first column would be A31. A12 would mean first row, second column. A22 would be second row, second column. And A32 would be third row, second column. Now, if matrices have only one dimension in one direction, we sometimes refer to them as vectors, but they're really just matrices that have only one dimension in them. A single number can be thought of as a 1x1 matrix if need be. And you can make matrices all the way up to n by m. So in this case, n rows and m columns. And you will often see them when they're very big and sort of indeterminate, represented with these ... dots in different places. Now, these square brackets or these round brackets don't actually make any difference whatsoever in terms of whether this is a matrix or not. In these examples, this is a 1x1 matrix. This is a 2x2 matrix. This is a 1, 2, 3, 4, 5 by 1 matrix. That's a typo. This is a 2x2 matrix. This is a 2 by 1, 2, 3, 4 matrix. And then this is our m by n matrix. So it's just a generic matrix. You can see that this is actually an m by n matrix. There are n columns and m rows. Now, matrix notation, typically we will refer to them with capital letters, and you will sometimes see them in print with boldface as well. Although when people are writing on the board, obviously we can't do boldface on the board. But in print, you will sometimes see them as boldface. Same thing for vectors. They will sometimes be represented in boldface, but with lowercase letters. But typically matrices are capital letters and vectors would be treated with lowercase letters. Sometimes you will see them generically referred to by a single arbitrary entry. So in square brackets, Aij, particularly when you have like a general formula for representing the entries of that A matrix. The lowercase letter for the entry will be matching the capital letter for the entire matrix. So matrix capital A would have entries lowercase a with subscript ij to represent which row and column they belong to. Letters with paired subscripts like A11 and A22 always represent entries of a matrix. And when they're the same value, then they're on the diagonal. Now, we can also describe rows or columns of a matrix. And so typically we would represent rows as row sub 1, R sub 1 as row 1, R sub 2 as row 2, etc. And similarly for columns, we would number them 1, 2, 3, etc. C sub 1 for column 1, C sub 2 for column 2. We're going to be using these row and particularly the row notations later on when we start talking about operations on matrices. Now, there are some special matrices that are worth keeping in mind. The identity matrix is a matrix that has ones on the diagonal entries, so the ones where the subscripts are the same, and zeros everywhere else. So these are some examples: a 1 by 1, a 2 by 2, a 3 by 3, a 4 by 4. Identity matrices are always square, so it has the same number of rows as columns. And when you multiply any matrix by the identity, you get the same matrix back again. So it acts like a 1. That's why it's called the identity. We will see when we deal with our treatment of inverses later on that when you multiply a matrix by its inverse, you get the identity back. The zero matrix is just a matrix that contains all zeros. And again, if these can be square or rectangular, unlike the identity matrix, which is always square. This is just typically in a problem where you're multiplying matrices together. The zero matrix will be specified as simply whatever is the size is necessary to obtain the multiplication to be defined. But anytime you multiply a matrix by a zero matrix, you get the zero matrix back again. So again, it works like a zero in multiplication. And we'll talk in another video about how matrix multiplication works. There are also triangular matrices. Now, triangular matrices have certain special properties that make it useful for certain kinds of operations. Triangular matrices basically have entries that can be non-zero on the diagonal and then non-zero on one side of that diagonal, but not on the other side. So for this particular example, it's non-zero above the diagonal, but all zero below the diagonal. This would be called an upper triangular matrix. In this example, again, here's the diagonal. And then below the diagonal, we have non-zero values, but above the diagonal, we have zero values. This would be called lower triangular. And obviously, any 1 by 1 matrix would automatically be triangular because there are no other entries except that one diagonal entry. This would be an example of a 2 by 2 triangular matrix. Again, this would be upper triangular because here's the diagonal, and below the diagonal is zero, and above the diagonal is allowed to be non-zero. Now, you can also have diagonal matrices where there are only non-zero entries on the diagonal. So A11, A22, A33, etc. And so these would be examples of that. The diagonal entries themselves may be zero. They don't have to be, but they can be. But then on either side of the diagonal, everything else is zero. So here we have our 3 non-zero entries on the diagonal, and then above the diagonal and below the diagonal, they're both zero. So you can think of these as both upper and lower triangular, or the special case of a diagonal matrix. These are also very, very useful for doing calculations that are relatively straightforward. And so these are very popular types of matrices. We're going to talk in linear algebra about methods for converting a matrix into a diagonal matrix if possible. Now, any matrix that has both the same number of rows and the same number of columns are referred to as a square matrix. Some kinds of matrices have to be square, like identity matrices. Not all matrices are required to be square, but triangular and diagonal matrices are types of square matrices. We can also work with what are called augmented matrices. We're going to see when we set up our systems of equations that typically when we have a system of equations, we'll put the coefficients in one matrix and then the solutions in another matrix, another vector. And when we put them all into a single matrix, that is called an augmented matrix. So it has both the coefficient and the solutions in the same matrix entry. We're going to look at in another video how to do row operations in order to solve systems using an augmented matrix as one of our solution methods for working with matrices. Now, in the next video, we're going to continue to talk about matrices by talking about operations on these matrices.